Good day and welcome back for part 4 of our discussion on evaluating trigonometric integrals. So recall from our previous discussion, we've worked at developing techniques for integrating functions of the form sine to a power times cosine to a power, or tangent to a power multiplied by secant to a power. And in either case, we've developed some rather nice what we refer to as power reduction techniques. And in this video, I would like to go through two more such examples, one of them that might have a slightly different appearance to it, but we will see that the same techniques we've previously discussed can be applied. And then in our final video on this topic, we'll look at a few more involved examples. But regardless, make sure you're spending some time working suggested problems from the textbook. And if you have questions, let me know. So let me begin with some reminders. A few trig identities we need to be familiar with. The first two are what we might think of as the half angle identities, or you might refer to them as the double angle formula for cosine. And note the subtle difference in the formulas, as we've indicated previously. With cosine squared x, it's a positive sign, and with the sine squared x, it's a negative sign. In terms of Pythagorean identities, I find that students typically can very quickly recall the standard Pythagorean identity. Cosine squared plus sine squared equals 1. But let me remind you, we can very easily modify this to get the other Pythagorean identity. If we simply divide each and every term by cosine squared x, we get an equivalent version of this Pythagorean identity. 1 plus tangent squared is secant squared. So let's go ahead and start off with what I hope is a familiar example. Let's integrate tangent multiplied by secant to the fourth. And recall our thought process. Because there's an even power of secant, we can pull off a secant squared and save that to be our du. So starting off with our intuition, we are going to pull a secant squared, pair it with the dx, and our goal is that the secant squared dx will be du. Note, in order for du to be secant squared x, u would have to be tangent. And because that original power of secant is even, when we've pulled off a secant squared, there's still an even amount of secants remaining, and we can rewrite those in terms of tangent using the Pythagorean identity. So note, secant squared x can be written as it is above. And this technique that we've used is something that I will refer to as a power reduction technique. We've, in a sense, reduced this power of secant in a way that allows us to rewrite and do a substitution. So now, let's go ahead and finish. This should be the quick part of the problem. We make each tangent a u. Secant squared dx becomes our du. So we algebraically simplify our integrand by distributing. Then we anti-differentiate term by term. And then we resubstitute. So 1/2 tangent squared plus 1/4 tangent to the fourth plus c. And hopefully you can note just from the pace of the problem and the familiarity of the finish, once you get through this power reduction technique and you've identified the substitution which you are going to use, the remainder of the problem actually flows very quickly, and it's very similar to other examples we've worked. And just to reiterate, whenever we have an even power of secant, this is an approach we have that can work. Let's move on to our second example. In this case, we would like to integrate cosine cubed divided by the square root of sine x. And I realize this is not precisely in that form we've been working with of cosine to a power times sine to a power where the powers are whole numbers, but we do have some intuition we can apply. When we look at this integral, hopefully our first thought might revolve around something related to a substitution. You see this sign stuck inside the square root, inside the bottom of a fraction. Maybe we could get a substitution to work. But at the same time, maybe your first thought looking at it would be cosine cubed. We know exactly how to handle odd powers of cosine and sine using that associated power reduction technique. So either way will actually get us there in this case. I prefer to think about it from the substitution perspective. This really looks like it would be conducive to the substitution u equals sine of x. And if u is equal to sine x, du must be cosine x dx. So with that in mind, we can rewrite the cosine cubed as cosine squared times cosine, and then we still have that pesky square root of sine in the denominator. And at this point, what I would like you to do is go ahead and pause the video, give yourself 3 or 4 minutes, finish up this example. And hopefully at this point you've gone to the trouble of pausing your video and working through the details. Remember, that's a very important part of the learning process. So if we want to make the substitution u equals sine x, this cosine squared needs to be expressed in terms of sines. And we can do this using the Pythagorean identity. Cosine squared is 1 minus sine squared. And now that we have rewritten by using this power reduction technique of pulling off a cosine, writing the remaining cosine squared in terms of sines, we're ready for our substitution. Making each sine a u and cosine x dx our du, we see very quickly that our integrand will become 1 minus u squared divided by, and I'm going to write the square root in terms of a power, u to the 1/2, du. And note, this is a very familiar calculus problem. If we can get the integrand solely in terms of powers of u, we are good to go. So breaking this fraction up over that difference in the numerator, we can write this as u to the minus 1/2 minus u to the 3/2. Now we go ahead and we anti-differentiate term by term. And just to make sure there's no confusion with the integration, we're anti-differentiating terms of this form x to a power. So we'll get back 1 over n plus 1 x to the n plus 1, as long as n is not minus 1. Note in this first term we have n equals minus 1/2, and in the second term n equals 3/2. So with the first term, minus 1/2 plus 1 is 1/2. So we get back 1 over 1/2, which is 2, u to the 1/2, minus, in that next term, n is 3/2. 3/2 plus 1 is 5/2. 1 over 5/2 is 2/5. So 2/5 u to the 5/2 plus c. And then as usual, we finish by resubstituting. So I'll write this as 2 square roots of sine x, which you could leave as a 1/2 power, minus 2/5 sine x to the 5/2, all plus c. And this completes our example and the current discussion. In the final installment on this topic of evaluating trigonometric integrals, we'll look at a few more involved examples. So stay tuned and take care.